Our topic today is the notion of the slope of a line. The slope of a line is going to be a number that describes how steep the line is and in what direction it goes, whether it rises or falls as you move from left to right on the graph. So let's think about what a line looks like. If we take a graph like this, and let's say we've got a line here. What I want to do is I want to look at two different points on this graph, and I want to do the same sort of thing we did last time when we were looking at the distance between 2 points. And I want to consider this triangle. Now this right triangle here connects up the 2 points that we're looking at. And so let me label these. I'll label this first point x1, y1. This second point x2, y2. And let me take one more point up here, x3, y3. And I also want to draw another triangle that goes from the point x1, y1 up to the point x3, y3. Now let me go ahead and give these names, these points some names so that I can talk about them more specifically. So A, B, C, let me call this point D, let me call this point E. So let me also label the lengths of each of the sides of these triangles. Now again, based on the sort of analysis that we did last time, we can do this as follows. The segment BD, the vertical side of the smaller triangle, has side length y2 minus y1. The segment CE has side length y3 minus y1. And the segment AD, the horizontal side of the smaller triangle, has side length x2 minus x1. And the segment AE, the horizontal side of the larger triangle, has side length y3 minus y1. So what I want to do is find some way of using these lengths to measure essentially how steep our line is. Now the steepness of a line can be described as the following way. To determine the steepness, we ask, how much does the y value of 2 points change for a given change in the x value? In other words, if I move some distance horizontally along the graph, how much have I changed vertically? We can really see why this would matter if we compare a couple of lines with different slopes. Let me take another just little cartoon down here where I'm going to take two lines that have different steepnesses. We're going to say they have different slopes. Now, what I want to do is I want to look at this point right here, and I want to see what happens if I move to the right by a certain amount. And we can see that if I do that, then the point on the blue line that I get sits there. So let's say I moved over by 1 unit. Well, then the blue line has a point which sits a certain distance above the original point I looked at, but the point on the red line sits higher than the point on the blue line. So even though when we move from the left point to the right point, we've moved the same horizontal distance, on the red line, we've moved a higher vertical distance. This corresponds to us looking at the graph and saying that, well, the red line is steeper, and we are also going to be able to measure that using the sort of triangle analysis that we have up here. We want to compare how much our y values change based on how much our x values change. The way that we're going to do that is we're going to look at the quotient, the ratio of the change in the y values divided by the change in the x values. Now, in order to make that make sense, I want to look at this example over here with the triangles and see what happens. Let's try using the change in the y values divided by the change in the x values. And I'm going to do this with a couple of pairs of points. I'm going to do this when I go from x1, y1 to x2, y2. And if I do that, then I see that when I move from x1, y1 to x2, y2, the difference in the y values is y2 minus y1. It's the vertical side of this triangle, the length of the vertical side of this triangle. And the difference in the x values is x2 minus x1. It's the length of the horizontal side. But of course, x1, y1, and x2, y2 are only two of the very, very many numbers or points that there are on this graph. So let's try again with a different pair of points and see if we get something different. Let's look at what happens if we compare the 2 points x1, y1 and x3, y3. In that case, we'll get y3 minus y1, because that's the length of the vertical side, CE, over x3 minus x1, because that's the length of the horizontal side, AE, which I just realized I mislabeled using y's. That didn't make any sense. Let me correct that. So it looks for a moment like we've got a problem, because if we try taking this ratio of the change in y's divided by the change in x's, it looks like we've gotten different answers because our two ratios here look like they're different. However, we can use geometry to say that they are in fact the same. These are equal, and this is since triangle ABD is similar. To triangle ACE. What this means is that if I take a ratio of lengths on ABD, that's going to be equal to the corresponding ratio of lengths on the larger triangle. Now we know that these two triangles are similar because they're both right triangles and they share this same angle down here at A. And that means that all three angles actually of the triangles are equal, or they're equal in pairs, and therefore the two triangles are similar. Therefore they have corresponding ratios. The point to all of this is that this computation, this formula using the difference of y's divided by the difference of x's, doesn't depend on which 2 points on the line you pick. You can take any 2 points on the line and calculate this number, and you're always going to get the same number. What this means is that this number that we calculate, which we're going to call the slope, is an essential component of the line itself, not of the any specific points on it. The line itself has a slope that you can compute using any 2 points on the line. So let's give a definition and then see how we can apply it and compute it and use it. So definition. The slope of a line is, well, we'll often denote it using the letter m, and it's equal to y2 minus y1 over x2 minus x1, where x1, y1, and x2, y2 are any 2 points on the line. I can take any 2 points on the line, look at the difference of their y values, and divide by the difference of their x values, and get the slope out of it. Now, there are a number of other ways that we sometimes write this down. We also occasionally use the following notation, delta y over delta x. And that's because this symbol delta means, or often means, change. Delta is the Greek letter D, and so we sometimes use delta to mean difference in a particular quantity. So when we write delta y over delta x, it means the change in the y values divided by the change in the x values between these 2 points. We also can write it out in words. This just means change in y over change in x. And sometimes in the very simple to memorize, rise over run. The idea being that rise is a word that suggests a vertical change, and run is a word that describes horizontal change. And so this is a number that we can associate to a line. So let's take a simple example. Let's find the slope of the line passing through the points 3, negative 4 and negative 2, 7. So you'll remember I mentioned when we did the distance formula last time that I mentioned you don't really have to pay close attention to what order you do things in, what order you subtract things in. Here you do. The order matters. Now, we can choose either one of these points to be our x1, y1, and either of them to be our x2, y2. I'm going to arbitrarily choose them this way. When we go to compute the slope, we're going to take the difference in the y values, and so in this case, this is going to look like 7 minus negative 4. So the y value for one of the points minus the y value for the other point, divided by, now we get negative 2 minus 3. So the point is that the 2 values that you get first have to come, that you list first on the top and bottom, have to come from the same point. So one of our points was negative 2, 7, and so those are the 2 points that we're using on the first part of our difference in the slope. And then the second parts also have to come from the same point, the second parts of the differences. So our second point, or one of our points on our line is 3, negative 4. And so we need to put 3, comma, -4, both together. So in particular, the thing that you have to not do, so the following is incorrect, we can't split them up and have the 7 come first on the top, but the 3 come first on the bottom. All right, this doesn't work because 3 comma 7 isn't one of our points. -2 comma -4 isn't one of our points. We need to make sure that whatever numbers we're putting first on the top and bottom go together in one of our points, and whatever numbers we put second go together as one of our points. As long as we do that, though, then we can work this out. So 7 minus -4 is positive 11, and then -2 minus 3 is -5. So we get negative 11 over 5 as our slope. Now, a negative slope makes perfect sense. In fact, whether a slope is positive or negative tells you something important about the line. Let's see what that is by sketching out what this line is that passes through 3 comma -4 and -2 comma 7. All right, so we had a point that went through 3 comma -4, this point right here, and then -2 comma 7. 1, 2, 3, 4, 5, 6, 7. And so here's the line. Here's the line that we got, and what we just found is that this has a slope of -11 over 5. Let's sketch out a few other lines here to see if we can tell what various values of the slope tell us about the lines in the graph. So let's take one that looks like the following. Let's take one that goes through the point -4, 0, and through the point 3, 3. Let's take this line. So now we can calculate the slope of the red line. So the first thing we want to do is we want to identify 2 points that it goes through. And in this case, we see it passes through the points -4 comma 0 and 3 comma 3. So the slope is m equals, now we can take the difference. So it's the difference of the y values on top. So I'll write that as 0 minus 3. So notice I'm using the point -4, 0 in the first slots. Those are coming first on the top and the bottom. And then I'm subtracting what I get in the point 3 comma 3. So -4 comma 0 is one of my points, and then 3 comma 3 is one of my points. So we're left with -3 over -7, which gives us 3/7. So this red line has a slope of 3/7. Let's do a couple more. Let's take -1 comma -1, and let's make a really steep one. Let's take the point 1 comma 11. Now this point is really steep, or this line rather is really steep, the green one. So let's calculate its slope. Slope of the green line, well, it goes through -1, -1, and 1, 11. So the slope is, this time I'll use 1, 11 first. So 11 minus -1 over 1 minus -1. So 11 minus -1 is 12. 1 minus -1 is 2. So we get 6 out of it. So in this case, we have a slope of exactly 6. And then finally, let's try one more line that goes through the point 0, 0 and the point 6, -2. So let's look at the yellow line. So it's the slope of the yellow line, which goes through 0, 0 and 6, -2. We'll take the difference of the y values, -2 minus 0, the difference in the x values, 6 minus 0, to get -2 over 6, which is -1/3. And so we have a slope of -1/3. All right, so we have 4 lines of various slopes and with various steepnesses. So I want to talk about what we can tell about these various lines given their slopes, or what we can tell about the slopes given the lines. So let me get another page, and let's look at this. So one thing that I want to start off looking at is what happens when the slope is positive versus when the slope is negative. So you'll notice that we have 2 positive slope lines. And we have 2 negative slope lines. And you'll also note that whether the slope is positive or negative corresponds to whether the lines themselves are increasing or decreasing. That is to say, whether their y values are going up or going down as we move from left to right along the graph. The positive slope lines have y values that keep going up. The points on the lines are getting higher and higher on the graph as we move from left to right. The lines with negative slope are getting lower. They're going lower on the graph as we move from left to right. And this goes back to thinking about what the slope actually represents. It tells you how much the y values are changing given a change in x. And a negative number means that it means basically that the changes in y's and x's are opposite each other. So if x is increasing, that is we're moving from left to right on the graph, then the y values are going to be decreasing. That is, the graph is going to get lower on the graph. Whereas if the slope is positive, that means that the x's and y's are changing in the same direction. They're either both increasing, which means you're moving to the upper right on the graph, or they're both decreasing, which means you're going to the lower left. So a positive slope means the line is increasing from left to right, meaning precisely the y values of points on the line are increasing as we move from left to right along the line. And then a negative slope means the line is decreasing. So that's the first thing that the slope tells us. It tells us whether the line that we're looking at is sloping up or sloping down as we move from left to right. There's another thing it tells us, though. Even among positive sloped lines, the actual value of the slope can tell us something, or it can help us to compare a couple of lines. So, for instance, let's look at the two positive sloped lines that we have here, the red and the green. The red line has a slope of 3/7, which is less than 1. The green line has a slope of 6, and so the green line has a slope that's significantly higher than the red line's slope. This also corresponds to a steeper line because, again, thinking of the slope as how much y changes for a given change in x, a slope of 6 means that for every 1 unit the x changes, the y is going to change by 6 on this green line. Whereas for every 1 unit x changes on the red line, the y value only changes by 3/7. So it's going to be much, much shallower. So what it looks like the fact is on the, well, just from looking at the lines with positive slope, is that a greater slope corresponds to a steeper line. And this is almost true, but we need to be a little bit careful. To see why we need to be careful, let's look at the negative sloped lines now. Now our yellow line has a slope of -1/3, and our blue line has a slope of -11/5. Now, remembering how inequalities work for negative numbers, we actually have that -11/5 is less than -1/3 because it's further to the left on the number line. However, we also have that the blue line with a slope of 11/5 is definitely steeper than the yellow line with a slope of -1/3. So to say whether a line is steeper or less steep than another one depends not only on how big it is, on which one of the two values is greater, but on how big they are. So I'll write it down this way. What we need to do is we need to look at the absolute value of the slope. So a line with whose slope has greater absolute value is steeper. So we say that the blue line is steeper than the yellow one because it has greater absolute value, or its slope has greater absolute value, I should say. And similarly, the green line has a greater steepness, is steeper than the red one because its slope has a greater absolute value. So combining the absolute value of a number with whether or not it's positive or negative, we get information both about the steepness of a line and about its direction, whether it's increasing or decreasing. So this is how we calculate slope. Let's talk about how we interpret this in some real-world types of scenarios. So, what I've said a few times here, I'll just make explicit here. A slope tells us how much the y value changes for every unit change in the x value. So, for example, if a line has a slope of 3 and the point 2, 1 is on the line, then let's look at another point. I want to look at what the point is on the line that has an x value of 4. Now, moving from 2 to 4 means we've increased x by 2. A slope of 3 means that for every change in x, the change in y is going to be 3 times that. So this is going to be increased by 6, since 6 equals 2 times 3. So if 2, 1 is on the line and the line has a slope of 3, then that means that the point 4, 7 is on the line. So the slope tells us how much the y value changes for every change of 1 in the x value. There are lots of things that we deal with in real life that can be described this way. For instance, let's look at the following scenario. Let's suppose you work at a job that pays $12 per hour. That means that for every 1 hour more you work, you gain $12 more on your paycheck. Let's live in a fantasy world for a moment where taxes don't exist. So, this means that the relationship between how many hours you work and how much you get paid on your paycheck is a linear relationship. And furthermore, this tells us that the slope of the line corresponding to that linear relationship is going to be 12. Because the ratio between how much change in the hours you work and the amount of money you get on your paycheck is 12. For every 1 hour you work, you earn $12 more on your paycheck. So in fact, we could even write down what this function is. In this very simple example, we have that if x is the number of hours you worked, and y is the amount of your paycheck, then in fact the relationship between them is very simple. It's just y equals 12x. And in particular, this means that we could go ahead and calculate the slope. We could get a couple of points on there, and we would find a slope of 12. This is the sort of thing that a linear relationship describes. It describes when every change in one variable corresponds to a proportional change in another variable. All right, so let's see let's see another application of this. So, the average rate of change of a quantity, or of a function, I should say, of a function f over an interval AB is given by the following formula. F of B minus F of A over B minus A. And let's see what's going on here. So the idea here is that we've got some function f, and we could plug lots of different numbers into it. And in particular, we could plug in two numbers a and b and ask, well, how much does the function change over this interval? And the change in f, which we could write as delta f, is just the difference in the outputs of f. And then the change in the inputs, which I will write as delta x, can be written this way. It's just b minus a. This is very abstract the way I've written it. Let's look at a specific example to see what's going on, and then we'll see what the connection is between this and slopes. So let's say my odometer on my car read 12,000 miles at 8 o'clock a.m. and read 12,840 miles at 8 o'clock p.m. What was my average speed? From 8 o'clock a.m. to 8 o'clock p.m. So one way that we can set this up is to use a function. So let's let f of x be the odometer reading at x hours after 8 o'clock a.m. All right, so x is the number of hours after 8 o'clock p.m. Yeah, sorry. So if we want to find our average speed is going to be the distance that we traveled divided by the time that it took us to do that traveling. So our average speed here is going to be the distance traveled divided by the time taken. And that's going to be, well, one way that we could write that down is the following. The distance traveled is going to be the distance in the odometer readings between the beginning of the trip and the end of the trip. Now, the beginning of the trip corresponds to an x value of 0 because at 8 a.m., well, we're 0 hours after 8 a.m. So f of 0 corresponds to the odometer reading at the start of the trip. F of 12 gives us the odometer reading at the end of the trip. The end of the trip happens 12 hours after the beginning of the trip. And so the difference in the two odometer readings will be the total distance that I traveled. The time taken is then the difference in the times. So in this case, my time taken is being measured in terms of x, where x is the number of hours after 8 o'clock a.m. And again, the end of the process occurs 12 hours after 8 a.m. And the start of the process happens 0 hours after 8 a.m. So this is how we could write this down, calculating the average speed in terms of this more general average rate of change definition above. Well, let's look at each of these things. F of 12 would be the odometer reading at 8 o'clock p.m. Well, we know that that's 12,840. F of 0 is the odometer reading at 8 a.m. That's 12,000. And the time taken, well, we already had that down there. That's 12 minus 0, which is 12. Now, finishing this up, 12,840 minus 12,000 is 840. 840 divided by 12 is 70. So this means that my average speed was 70 miles per hour. Now, of course, this doesn't mean that I was traveling at exactly 70 miles per hour the whole time. Sometimes I was traveling faster, sometimes I was traveling slower, but my average speed is what I get when I just take the distance that I traveled divided by the time that I took. Let's see what happens if we try to sketch out what's going on in this problem on a graph. So for this graph, I'm only going to use the quadrant 1 of the plane because those are the only numbers I'm looking at are positive. So x is the number of hours since 8 a.m. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Now, in this case, I am going to use a different scale for my vertical axis than normal. And that's because my y values, my function values for this problem are 12,000 and 12,840 and things like this. And if I use the same scale, my graph would be way too tall to be to really be visible. So instead, I will scale up differently. So I'll make this 1,000. Oh, I'm sorry. I want that to be 4,000, 8,000, 12,000, 16,000. So every tick mark horizontally corresponds to 1 hour, and every tick mark vertically corresponds to 1,000 miles. So now I can sketch out some points that correspond to the inputs and outputs of my function. So what I know from the problem is that f of 0 is 12,000. And that means that the point 0, 12,000 is on the graph of the equation y equals f of x. So one of the points on my graph is here at 0, 12,000. And then I also know that f of 12 equals 12,840. And that tells me that 12, 12,840 is on the graph. Now, I'm going to have to approximate this because Of course, I don't have 840 exactly listed here, but I can sketch out 12, 12,840. And my odometer reading, as I move from the left point to the right point, could do lots of different things. I'm just going to sketch out a few of them there. It could be that I hardly moved at all for a while, and then went to the end. I could have done a whole lot of movement at the beginning and then come up. I could have done something really weird where I somehow run my odometer backwards and get to the end point. There's a whole lot of movement that I could have done, a whole lot of different ways that I could have gotten from point A to point B, from the start to the end of my trip. However, if I draw a line, if I just draw a line between my starting point and my ending point, then the slope of this line is going to be 70, which is the average rate of change. And so the point here is that the average rate of change of the function f on the interval from a to b is the slope of the line through the points a comma f of a and b comma f of b. So the slope is a rate of change, and in applications we often use it to describe an average rate of change. The rate of change that you would have to constantly maintain to get from the starting point and ending point that you measure. So this is something that we use a lot. We can use slopes, as we've seen, for situations like the paycheck we saw before, where every increase in your input variable x corresponds to an exactly proportional increase in your output variable y. And in that case, your relationship is truly linear. But then we can also use it to describe the average rate of change of a quantity over time. So let's look at a couple more topics involving the slopes of lines. Let's talk about parallel and perpendicular lines. And the way that we detect parallel lines using slope is pretty straightforward and pretty intuitive, which is nice. Let's say I've got two lines and they have and they are parallel to one another. Let me try and sketch this out so that they're parallel. Well, if these two lines are parallel to each other, then let's look at what happens when I compare a couple of points that have the same x value on the two lines. Like this. Now, if I try to measure the slope of the blue line, I will take the rise over the run. I'll take the change in the y values of these 2 points and divide by the x values of these 2 points. And then let's look at what happens if I compare that to the slope that I get when I look at the red line. And what you'll see here is that if these two runs are the same, if the two horizontal distances that we change when we move from one point to the next on the two lines are the same, then the rise is going to be the same also. And that's because they're parallel, because they exactly match each other. Every rise on one line corresponds to exactly the same rise on the other. So we'll be able to prove this when we start working a little bit more with the equations of lines in the next section. But for now, we will use the fact that two lines are parallel if they have the same slope. And that's it. And then if two lines have the same slope, then they are parallel. So let's ask the question. Let's say, are the lines given by the equations 3x plus 4y equals 7 and y equals negative 3/4 x minus 12 parallel? So to work this out, we want to find the slopes of both of these lines. Now, we will have somewhat easier ways of working this out later, but for now, let's do that by finding some points on the lines and computing the slope. So let's look at 3x plus 4y equals 7. So one common way that we know of finding points on a line, especially when it's in standard form like this, is to find the intercepts. So if x equals 0, we get that 4y equals 7, which means that y is equal to 7 over 4. So that means that the point 0, 7/4 is on the line. And then if y equals 0, we get 3x equals 7. So x is equal to 7 over 3. So that means that 7/3, 0 is on the line. So that means that the slope of this line is the difference in the y values divided by the difference in the x values. Now, make sure, as always, that you are subtracting things in the right order. So we take 7/4 minus 0, but then the x value that corresponds to 7/4 needs to come first in the denominator. 7/4 was a point, and the x value that went along with that had 0 as its x value. And so then we'll subtract the x value from the other point. So we get 7/4 over negative 7/3, which gives us negative 3/4 when we simplify all that down. So that tells us what the slope of the first line is. Now, if we go through the same process on the other line, if we plug in a couple of points for the second line, we'll be able to figure it out. Now, let's go ahead and do that. And I've run out of space a little bit here. Sorry about that. Let's look at y equals negative 3/4 x minus 12. Now, one trick that I would recommend you take advantage of, especially when you're working with lines that are expressed in this form, which we'll have a name for in the next section, is try picking x values that cancel the denominator of the coefficient of x. So x equals 0 is always a good choice. If x is equal to 0, then that means that y is equal to negative 3/4 times 0 minus 12, which is 0 minus 12, which is negative 12. And that means that the point 0 comma negative 12 is on the line. And then for the next x equals, I wouldn't just pick a random x. I would look at this fraction that's being multiplied by x, and I'd think, it's got a 4 in the denominator. I would like my x to be a multiple of 4 so that we get some cancellation there and not have to deal with the fractions, because fractions are often a bit of a pain. So let's try just using x equals 4. If x equals 4, then we get y is equal to negative 3/4 times 4 minus 12. Now, if we take 3/4 times 4, that's actually 3/4 times 4 over 1. The 4's cancel, and we're left with negative 3 minus 12, which is negative 15. So that means that the point 4 comma negative 15 is on the line. Therefore, we have that the slope of the line is going to be, let's do negative 15 minus negative 12. Always make sure to get all your negatives in. So negative 15 minus negative 12 divided by 4 minus 0. Now, negative 5 minus negative 12, negative 15 minus negative 12 is negative 15 plus 12, which gives us negative 3 over 4. Now, what you will notice here is that the slope of the line that we computed, in fact, shows up in the equation of the line that we worked with up above. That's no accident, and we're going to be using that fact very often as we move forward in the understanding of linear equations and linear functions. But for now, we can compare the slopes that we got for our two lines. The line that we described here has a slope of negative 3/4. The slope of the other line was also negative 3/4. And therefore, that means that the two lines are parallel. And that's really all there is to it. If you can compute the slopes of two lines and find that they are exactly the same, that means those two lines were parallel to begin with. Now let's talk about perpendicular. So remember that two lines are called perpendicular if they intersect and form a right angle. So if I've got a line like this and then a line like this, if they form a right angle, then they're called perpendicular. This, working out what exactly the condition is on slopes for two lines to be perpendicular is not quite as straightforward as working it out for parallel. And we're not going to try to prove it here. Again, we may return to that in the future. We can take a couple of examples though. So it turns out that a line with a slope of 1, having a slope of 1 means that for every unit you move to the right on x, you move up by exactly that same amount on y. So a slope of 1 essentially goes up at a 45-degree angle. So we could imagine that our blue line here has a slope of 1. It looks to be approximately that way. And a line with a slope of -1 has a makes a 45-degree angle with the horizontal, but it's going to be decreasing. It's going to be going down as you move from left to right. And those lines are certainly, we expect them to be perpendicular because they both form a 45-degree angle with the horizontal, but in different directions. So they should form a 90-degree angle with each other. So that gives some credence to the following theorem, but again, we're not going to prove that theorem, this theorem right now. We're just going to use it. So, if the product of the slopes of two lines is -1, then the lines are perpendicular. And if two lines are perpendicular, the product of their, or I'll write it this way, their slopes are negative reciprocals of each other, which is really just another way of saying that their product is -1. But the negative reciprocal of a number means that, so the reciprocal of x would be 1 over x, and whatever it was before, whatever number it was before, if it were positive, it becomes negative, and if it were negative, it becomes positive. Or if we're starting with a fraction to begin with, a over b, the reciprocal of that number is b over a, and then, again, we want to change the sign, make it negative b over a. So two lines can be seen to be perpendicular by comparing their two slopes to say, are they negative reciprocals of one another? So, for example, we saw that the line y equals -3/4 x minus 12 has a slope of -3/4. We saw that already. And if we continue working with the understanding that the coefficient of x in an equation like this gives us the slope, which is true, we'll see that later. The line y equals 4/3 x plus 1 turns out has a slope of 4/3. Now, 4/3 and -3/4 are negative reciprocals. And therefore, these two lines are perpendicular. Or to be more precise, the lines defined by these equations are perpendicular to one another. We are going to return to the question of perpendicular and parallel lines in the next section, where we start looking at actually describing the equations of lines given their points or properties, such as being parallel or perpendicular to something else. All right, the last topic on slopes for today is the question of horizontal and vertical lines. Now, horizontal lines are pretty straightforward. So let's look at that. Let's take a horizontal line and compute its slope. So let me take a horizontal line. To compute its slope, we just need to take any 2 points on the line. So let me take this one, which looks to be 1, 2, 3, 4, 5, 6, 7, negative 8, comma 4. And this one over here, which is 3, comma 4. Computing the slope shouldn't care about which points you take. And so the slope of this line will be the difference in the y values, so that's 4 minus 4, over the difference in the x values, 3 minus negative 8, which will give us 0 over 11, which is 0. So we get a slope of 0 here, which is consistent with our intuition about what the slope means. The slope is supposed to measure how much the y values change as you change the x values and move along the line. Well, if the line is horizontal, that means that the y values don't change at all as you move from left to right along the line. That means that no matter what change in x you get, the change in y is always 0, which means that to find your change in y, you take your change in x and multiply it by 0. So the slope is indeed is 0, which gives us the change in y for every change in x, because the change in y is always just 0. All the points have the same y value. So we have that any horizontal line has slope 0. Now let's look at vertical lines. Let me do the same sort of thing. Let's get one example, and we'll see that the example we choose will explain everything about the situation. So we've got the point -1, comma 7. And we have the point -1, comma -2. And the slope of this vertical line will be the change in y's, so that'll be 7 minus -2, over the change in x's, which is -1 minus -1, which gives us 9 over 0. Well, we can't put zeros in the denominator. This is undefined. So the whole intuition about what the slope means, it's how much the y changes as you change the x, completely breaks down when we start looking at vertical lines. Because the x never changes. And so it doesn't even make sense to ask how much does the y change as the x changes. The x never changes. And so the slope of a vertical line is undefined. We can't attach any real number to it and have it make any sort of sense. So the slope of any vertical line is undefined. Now I want to make absolutely sure we're on the same page here. Undefined does not mean 0, first of all. 0 and undefined are very, very different. Slope of 0 means you have a horizontal line. Undefined slope means you have a vertical line. Undefined also doesn't mean infinity. So in certain contexts, if we're being a little imprecise, in other disciplines, people may occasionally describe vertical lines as having a slope of infinity. This is a problem for several reasons. First of all, infinity is not a number. And so the way that we work with slope throughout all of mathematics relies on slope being a number, and infinity is not a number. Therefore, it doesn't make sense to say that the slope is infinity. Worse than that, though, there's no reason why you should prefer calling the slope infinity instead of negative infinity. So there are at least 2 different things that you could use to describe the slope, and that's before you even consider the fact that neither one of those are numbers. So, in algebra, in mathematics, a vertical line has an undefined slope. And we don't say any more than that. It has undefined slope. So that's most of what you need to know about slopes of lines, at least before we start getting into calculating it directly using equations of lines and moving beyond just plotting points.